Ladies and gentlemen, can I have your attention please, and we get started. Good evening everybody, and welcome to this evening's lecture, which is entitled Windfarm Design, Construction, Concrete and Peat. I will tell you more about that in a moment. However, just before I do, there are a number of the usual housekeeping notices that I must go through. As you know, the fire exits, there's the door that you came through, and there's one down there, and there are two down at the back of the room, down on that side. Don't forget, please, your mobile phones, turn them off or put them on silent. There's an attendance sheet outside the door. Please, if you haven't signed it on the way in, please make sure you do so on the way out, because in terms of liaising with Clyde Road, we like to illustrate to them just how active we are in the type of attendances that we get at our lecture. So please sign it on the way out if you haven't done so already. Other future events this day week, there's a lecture which is entitled Modular and Panelized Construction, which proves it's likely to be quite interesting, I believe. So that's this day week in this same venue. The following week, there's a lecture entitled Flood Risk Management. Again, is taking place in this room 2 weeks from tonight. And the annual dinner of the region takes place on next Friday week, which is the 8th of February. It usually proves to be a very enjoyable night to all of those who come along. So it's not too late to book. You can book in a variety of ways. It's on the Engineers Ireland Cork website, or it's actually myself, John Lochner, is the person who's organising it, so you can come to me afterwards if you want to. And so we move on to tonight's lecture, which is entitled Windfarm Design and Construction, Concrete and Peat, and it's given by three speakers from Malachy Walsh Partners. We have Brian Sayers, Sean Doyle and Cormac Murphy, and between them they have vast experience for over a long number of years of designing these wind farms and all that goes with it. And I expect that we will be enlightened very much by what they have to say to us. They will talk about themselves at the outset, so I'm not going to give you their CV at this point. And without further ado, I'll call on our first speaker, who is Brian Sayers, to come forward, please, and deliver a part of the lecture. Brian. Thanks, Brian.
Thanks very much, John. Good evening, and thank you all for coming. So my name is Brian Sayers, and I'm joined by Sean Doyle and Cormac Murphy. I'm from Malachy Walsh Partners Limerick office, and Cormac and Sean are from our Tralee office. So Malachy Walsh Partners started in wind farm design about 13 years ago. And since then, we've been involved in approximately 500 renewable energy projects, covering everything from wind farm construction, obviously, to pump storage, some solar farms, tidal barrages, and things like that. So in the last 5 years, we've had an involvement in about 50% of all wind farms built in Ireland, and we've designed wind turbine foundations on 4 different continents. We were hoping to make it 5. This project that you see here was a submission we did with Enercon, the wind turbine manufacturer, and that was for the first wind farm in Saudi Arabia, believe it or not. But it didn't go anywhere in the end. So the title of our presentation tonight, Windfarm Design and Construction, Concrete and Peat. We chose to talk about concrete and peat because we found over the years that the majority of the problems that we have come across during wind farm design and construction have been related to one of the two of these. So I'm going to talk a little bit about wind turbine foundations and issues that we have encountered during the design and the construction of the foundations. I'm not going to bore you by going through the Eurocodes line by line. That's something that Sean has planned for you. But try and stay awake, because Cormac has some very good stuff on peat at the end. So just before we start, could we just see how many people here have had some involvement in the actual design of a wind turbine foundation? We have a show of hands. So very few, 5, I believe, and Sean 6. So for people who haven't gone through that design process, it can be difficult to have a feel for the kind of forces and moments involved. The first time you get a wind turbine manufacturer's loading document and you open it up and you see the applied bending moment, it's a magnitude that's really quite amazing. And I suppose, you know, it's a magnitude that nobody really comes across in other areas of engineering in their entire career, really. It would be very unlikely that you would come across similar kind of forces in, you know, the kind of bridges or buildings that we would be involved in here in Ireland. So just to try and explain, I suppose in a more straightforward way, the magnitude of these moments involved, I've just set up this kind of theoretical question. And if you could imagine that we're here in the hotel in Rochestown, and in the field next door we build this gigantic block of concrete. We stick a wind turbine tower into the side of it, and we stick a little car on the end. What kind of distance do you think this car would need to be from that block of concrete before you'd start to get the same forces and moments that you get in a typical wind turbine? Anybody like to take a guess? I'll pick somebody if nobody. Donna Coleman down there, lecturer in structures and CIT. He'll surely know the answer. Yeah, not a bad guess. In fact, it's probably about 20 kilometers. So your car would actually be here out over the coast down by Kinsale somewhere. So it's a cantilever. Yeah, a car on a cantilever that's 20 kilometers long. So the kind of foundation that you need to have to hold up one of these turbines, you'd obviously expect it to be quite massive, heavily reinforced, you know, pushing the limits of engineering design. So this is one of the first ones that was built in the country, and you know, I presume it's still standing. I haven't heard anything different. This is one of the first ones that we were involved in, and you know, the things you'll notice. First of all, it's square. You'll see we have made an attempt to put in kind of radial bars here, but by and large we have these orthogonal mats. And you'll see that we have these holding down bolts known as an anchor cage. Foundations were also built with these cans, and a can really is the bottom part of a tower, and it gets placed into the foundation, and these radial bars are threaded through the little holes, and you know, you can see we still didn't take a hint. We still put this orthogonal mat on top of them, and this, you know, these cans have caused lots of problems over the years, and anybody here that has had an involvement in foundation design, they know exactly what I'm going to talk about. But these cans needed a sealing detail to stop water from getting down the interface between the concrete and the can itself. And the sealing detail was, you know, a standard detail given out by all the different wind turbine manufacturers, and you didn't deviate from it. And you know, you can see that the workmanship is really quite good. And you know, given that you know, this man might have been doing this up on the top of the mountain at you know, -4 degrees, you know, the workmanship really is not bad. But nevertheless, these cans did leave water in. The sealing detail invariably failed quite early on, and you know, water got down onto this flange, and you know, the rocking motion of the tower put this water under immense pressure, and it was confined. You know, it couldn't escape back up quickly enough, and it actually started to cause hydrodemolition of the concrete on top of the flange and at times underneath it as well. And one of the telltale signs that this was happening, outside of the fact that your tower was starting to lean more than it should, was this kind of paste that got brought up with the water, and you'd see it inside in the can here. A second telltale sign, you can see this little wedge of concrete that just cracks off, and as the can is moving up and down, it just pulls on this radial bar here, and it just cracks off this little wedge of concrete. You can make out this crack running along here, and you know, if you did a hammer tap survey on that formation, you'd hear very easily that concrete had burst. And interestingly enough, 9 times out of 10, you see this failure on the southwest to the northeast axis, which I'm sure you can guess is our prevailing wind. So a little video here. So you can see the pumping action of the water coming out. I think you can see the same over here as well. So, you know, wind turbines are designed for 10 million cycles, so you can imagine the destructive effect of that happening, you know, 10 million times over 20 years or whatever it may be. This is just another one showing a similar kind of thing. So without seeing this moving, you can see just from the dirt marks, you can see the difference in height here. This is an emergency shut off, when the turbine is just shut off very quickly, and you can see this just rocking in its foundation. So obviously our clients were not happy with this, and they wanted to know what was going on down inside in that foundation. So we were involved in some investigative works. We drilled some holes down and stuck in a camera to see what exactly was going on. And it starts. It's going to start. So what you would see is you'd see voiding on top of that flange. You'd see a void underneath it, and those voids are like an annulus going the whole way around that foundation, and it just allows that can to move up and down. And obviously you have to go back and you have to grout it up and just pin it back into place. So this is where we're at today. You can see the foundations now are circular. Cans aren't used so much anymore. We use these anchor cages pretty much the whole time. The plinths have all this congested reinforcement, which is where all the stresses really are concentrated. You know, the main reinforcement is radial, and you have these circumferential bars going around. These, by the way, are not actually hoops. It's just one big spiral from start to finish. It's about 2 kilometers long, and it's just an awful lot easier for guys to fix reinforcement when it's like that. So another problem that we came across on a number of foundations, we had these reflective cracks, and you know, they were located over the reinforcement below. They're reflecting the positions of the reinforcement under. And we had these weep holes, and these weep holes were leaving water out for maybe 2 or 3 weeks after the foundations had been poured. So it was clear that it wasn't bleed water coming out of the mix. You know, when we looked at it, we saw really that the only source of water was this water that you can see here ponding in what's called a grout well. This is the grout well here, and it's just a rebate in the concrete. It's filled up with a high strength grout, and the tower sits down on top of it. But we suspected that you know, as the concrete was curing, that maybe it was shrinking and just pulling away from these anchor bolts and just allowing water to get down to this level here. The reflective cracking is plastic settlement cracking, and it's synonymous with deep pores, and the concrete just settles into itself, and it kind of breaks its back over the top of the reinforcement. So we suspected that if there was plastic settlement cracking, then there was a very good chance that underneath these radial bars, you were getting a very small little gap that was just acting as a conduit to allow water to make its way down to here. And once water got down here, and you had this hydrostatic pressure just burst up to the surface, and it it manifested itself as a weep hole. So again, of course, our client wanted to know what was the meaning of all this. If you had a gap underneath the reinforcement, then you had a loss of bond, and if you have a loss of bond, you have a loss of tensile capacity and a loss of strength in the foundation. So we had to carry out some repairs. Let's see, does this work? So you can see here we decided to inject all the cracks. These nipples were glued on. The crack was covered over, and our resin was injected. And you can see here as the resin is injected here, it pushes water along the crack, and you can see water coming out of this nipple, and then it'll move along to the next one. And really, the quantities of water coming out from a hairline crack, it was quite astonishing. You can see it coming out here now, and it'll make an appearance here in a second. So after this was completed, there was an onus on us to prove that this had actually worked. So we took some cores down through the base, and what we saw was that the cracking, both sides were now well bonded to each other, and as we suspected, there was a very small void underneath the reinforcement, and this was now well filled with an epoxy that was giving back the bond that you would expect from a new foundation. So the last thing I'm going to talk about, and just one aspect of geotechnics. To the best of my knowledge, there hasn't been a geotechnical failure under a wind turbine in Ireland so far. I'm not sure if would you agree?
Not geotechnical.
Not geotechnical. Speaking to experts that go around the world fixing problems with wind turbines, they say to us that they haven't seen any geotechnical failures under wind turbines, which is certainly very good to hear. This is not in Ireland. I don't know where it is, but the worst thing about this, for the engineer involved, is not that this toppled over, is that there's probably another 25 of them around here that have exactly the same foundation, which is always a risk when you design wind turbine foundations. So this is just a typical excavation that you would see on any wind farm in Ireland. You have a hard bearing stratum at this level. It might drop off to another level, and you have to fill this up, and you have to check for differential settlement and rotations and static and dynamic stiffnesses and all that kind of stuff. But it's relatively well understood, and it's it's relatively straightforward to deal with. If you're lucky enough to get very hard rock close to the surface, as we were with this project, which is in the Highlands in Scotland, we found schist right up on the surface. They had big problems with concrete supply, so we did a very nice, small, neat foundation, and we just anchored it down to the rock, just pinned it down. The one geotechnical thing I want to talk about for a minute is the issue with resonance. And for people who don't know what resonance is, it's when something that's vibrating vibrates at the same natural frequency as something else. It transfers its energy into that other object. And you can see here that when the vibration of this table speeds up, and it's not, and the vibration matches the natural frequency of this guy. This guy stops, and this guy starts moving. And the same thing can happen with wind turbines. It's not an issue. It's not an issue for ground-bearing foundations, but it can be an issue for a pile foundation, and it is certainly an issue for offshore when you have monopile design. So we have had a project abroad where we've had, I think, 20-meter deep piles in ground that was very, very suspect. And you'll see that the Eurocodes say that you know, any ground where the undrained shear strength is less than 10 kPa doesn't give any restraint to the piles themselves. So you end up with a situation where the foundation, which sits on top of 20 or 30 meter long piles, which are effectively acting like stilts, and they're taking all the forces from a wind turbine. I suppose the possible sources of vibration, be it onshore or offshore, are the wind, obviously, and the period of wind is roughly 100 seconds, so the frequency is going to be down at about 0.01 hertz. Waves in the North Atlantic, they have a period of about 10 seconds, so they have a frequency of about 0.1. Every wind turbine has a vibration, and this vibration is known as a 1P vibration. And if the turbine rotates at maybe 5 to 10 or 12 revolutions per minute, you're going to have a frequency between 0.1 and 0.2. If the turbine has 3 blades, you get a 3P vibration, which is caused by the shadowing effect of the blades passing the tower. And the 3P vibration is basically 1P multiplied by 3. So with this knowledge, you have to make sure that the natural frequency of your wind turbine and its foundation does not fall within any of these zones, or you're going to get resonance. It's unrealistic to think that the foundation will be down here. It just isn't inflexible enough. To force it to be up in this zone means that you probably would have to make it very, very heavy, and it would be very uneconomical. So you're kind of stuck with forcing the natural frequency into this zone here. And the DNV dictates that you add 10% to these zones for almost like a factor of safety. So it narrows it down again, the zone that you have to place the natural frequency of the system at. And for those of you that are into geotechnics, you'll see that if you have a normally consolidated or an over-consolidated ground, you want to be aiming for this line here, because with the loading and unloading, that ground is going to stiffen up, and the natural frequency is going to move to the right. And of course, if you have an over-consolidated ground, it's going to do the opposite. It's going to move to the left. So I suppose just to conclude, I would just like to say that in Ireland there are probably only maybe 5 or 6 consultancies that are actually carrying out wind turbine foundation design at the moment. It's quite a small pool, and our designs are pretty aligned at this point in time. You don't see much variation in them, and I would say that as an industry we're pretty comfortable with where we are with foundation designs at the moment. We've been involved in foundation, with consultants in South Africa and the States and Germany and other places. And I think it's fair to say that in Ireland we don't lag behind when it comes to, I suppose, our expertise in designing foundations. And we've found that on more than 1 or 2 occasions we've been able to show them a thing or two and show them how they can make their own designs better. So that's me finished. I'll hand you over to Sean Doyle. Thank you very much.
My name is Sean Doyle. I work in the Tralee office of Malachy Walsh Partners, and I've been involved in various aspects of wind farm design over the years, including work on turbine foundations. That's me in the middle. So as Brian said, the wind turbines are subject to extremely large loads and very high overturning moments, and that's because, first of all, the turbines are very high. They need to be high where the wind is. The wind speed increases as you go up from ground level, and the force that the wind imposes on the turbines is very high. The function of the turbine rotors is to decelerate the column of wind. So I'm going to spend some time talking about the wind and those forces before I start talking about the foundations themselves. Like 15 or 20 years ago, the wind turbines were maybe only half a megawatt, 0.65 and then 0.85, but now most turbines are in the 2 to 3.3 range. That's what you generally find in Ireland. And these are the typical sizes. They can vary quite a bit, but a 3 megawatt turbine would typically be 80 meters high with 90 meter rotor diameter and tip height of 125 meters. The largest ones, like the Enercon E126, is very large in comparison. There's none in Ireland at the moment. But the hub height of an E126 is the same as the tip height of the 3 megawatt machines. So they're extremely large. So I'm just going to have a look at where all the force comes from. And it all comes from the kinetic energy of the wind. So if you want to see where this comes from, there's a law called Betts's law, which defines the amount of kinetic energy that you can extract from the wind. It was done by Albert Betts in 1919, and if you look up the great fountain of knowledge, Wikipedia, you'll come across these diagrams, and this shows a column of wind, and as it goes through the turbines, it decelerates, its velocity decreases, and it's that deceleration of the wind that causes the huge force on the rotors. So it's interesting to look up Betts's law. It's just based on conservation of energy and momentum. And basically, the more you decelerate the wind, the greater energy you get out of it. But there's a graph here that says that if you don't slow it down at all, you get no energy out of it. But the more you slow it down, you reach a maximum where when the wind speed decreases to 1/3 of its upstream velocity, you get the maximum yield, which is 59.3% of the total energy. Now, modern wind turbines, they can achieve 75 or 80% of this maximum, which is about 45% of the total. So in practice, the velocity is reduced to about 50%. So that's a huge amount of energy. The wind turbines start producing power at wind speeds of 3 meters per second, but they produce very little power at that stage. Most turbines reach their maximum power at 17 meters per second, and as the wind speed increases to 25 meters a second, the output remains the same, because as it goes up beyond 17 meters per second, the blades are turned out of the wind, and the Betts coefficient is decreased and keeps the output constant. If it didn't do this, the turbines would get damaged. So above a 10-minute average of 25 meters a second, the turbine shuts down. This is a power curve that I was talking about. This This particular one cuts out or reaches full power at 15 meters per second. It varies depending on the machine. Now this huge force I was talking about, the density of air is 1.2 kilograms per meter cubed. Most people would say that wind doesn't have any mass, but it is quite heavy in large volumes. So the 90-meter diameter rotor would have an area of 6,360 square meters, which is about 1.5 acres. And at a wind speed of 17 meters per second, there's 130 tons of air passing through it a second. And if that's slowed down to half its velocity, it's a huge amount of kinetic energy extracted from it. So essentially, that's where the huge overturning mass come from for the wind turbine. So for designing the turbines, the structural design of it, the manufacturers give tables of loadings, and they give operational loads and the extreme loads. Then the extreme loads are when the machines are at standstill. The SLS loads are the top 1% of the operational loads, and they only occur 1,750 hours out of the total lifetime of the machine. The ULS loads are based on gusts of 50 meters a second, which is 180 kilometers an hour. And they're the speed, or they're the wind speeds that the structural design is done for. The ULS is generally 2.5 or 3 times the SLS loads. So the unfactored ULS loads are commonly 100,000 kilonewton meters, which is, and Brian had spoken earlier about the magnitude of that. It's like a 100-ton load on a 100-meter cantilever. It's like having a trained locomotive on a 100-meter cantilever. And they're not the biggest ones. The 7.5 megawatt machines are 2.5 times that, or 250,000 kilonewton meters typically, which is enormous compared to what we normally have in the structures. So for the structural design, the overall stability, the criteria is that you have no lift-off at the edge of the foundation for the operational loads, and that you have no lift-off up to the center of the foundation for the extreme loads. This shows a diagram of the idealized uplift to the center of the foundation, which is about the middle 2/3 on the rectangular foundation. It's the middle. It's a bit. Go back to this here. It's for the circular foundation, the eccentricity of the load has to be within 3 pi over 32 times d, the foundation diameter. And this is the mathematics behind it. That's why that's the derivation of that formula. So when you design it, when you're designing for overall stability, you use those two factors to determine the overall size of it. And this is the finite element model that was done after that, which shows that there's very little loading here, but there's still full ground contact for the whole foundation. And here the lift-off is almost half of it for an extreme unfactored load. There's also checks done for lateral sliding and for rotation about the vertical axis, but these are never critical and have very high safety factors. Now, foundations were originally square back 10 or 15 years ago. The first one that Brian showed there was square. So then they progressed to octagonal, but now they're almost all circular because the loadings are symmetrical. They can come from any direction, so it makes sense to make them circular. Typical diameters are 17 to 22 meters, with concrete volumes of 350 to 600 cubic meters. Steel weight is probably 110 to 125 kilograms per meter cubed. So if you have 500 cubic meters of concrete, you'll have about 60 tons of rebar. This is just a finite element model that is used for the structural design. It's basically a set of 2D plates with defined thicknesses. The ground reaction is represented as a series of linear springs. And all the design is done in compliance with Euro codes. I think the only one of those are going to really is fatigue, maybe. These are typical rebar drawings. The design, this keeps moving. The design has radial and circumferential bars, which are very substantial amount of steel in them. This is the cross section. There's the radial bars with shear links, and in the center here, where we have a huge amount of compression from the turbine, there are horizontal shear links here to prevent bursting of the concrete. This is the bolt cage that holds down the turbine. Number of bolts can vary 44, 80, 90, diameters of 42 to 60 millimeters. And the lengths are typically 2.9 or 3 or 3.1 meters long. The bolts are tensioned before the towers go on. They're tensioned at the bottom section of tower on them. And they're not torqued. People refer to them as torquing bolts, but in fact they're stretched hydraulically, and the hydraulic pressure determines exactly what the loading is on the bolt. So they typically stretch by 5 or 6 millimeters. So the tension would be 300 to 600 kilonewtons. I think the last one I designed just recently was 600 kilonewtons per bolt on 80 bolts, 80 pairs of bolts. We've been involved in one recently with 60 millimeter bolts with tension to 950 kilonewtons each. Now the reason that they're pre-tensioned is so that you don't get any stretching of the bolt under the extreme loads. But the bolts are not bonded to the concrete, they're in a plastic sleeve, so all the tension goes down onto the bottom flange. This is a diagram here taken from an actual design document for the turbine we did a few years ago. Basically, if you didn't pre-tension the bolts, the stress strain line would be like this. But when you pre-tension it, it starts here. This one is 600 kilonewton load per bolt. And as the load is applied, it follows this line. So there's actually very little increase in the tension on the bolt, and very little increase on the load of the load on the anchor plate. When the bolt is tensioned by about 5 or 6 millimeters, the concrete compresses at the same time, but the concrete compression is probably only 0.3 of a millimeter. So when it gets the full load on it, the concrete relaxes, but it only extends by about 0.3 of a millimeter. And that's the only amount by which the bolt will extend beyond its original stretching point. So in this particular case, the tension on the bolt only went from 600 up to 600 up to 6, which is only a 6% increase in the bolt tension. So you get very little variation down at the bottom, and you never get the problems that Brian was talking about on the cans, where you get pulverization due to heavy cyclic loads. One of the things we have to design for is fatigue in structural design, because the loads are completely cyclic and it's non-stop cycling for 20 years. So if you haven't been involved in fatigue design, this is the basic diagram and table from Eurocode 2. And the basic parameter is the number of cycles, or the stress at which a million cycles will cause failure. So in this case, with a million cycles there, that will cause failure, but equally a lower level of failure with a higher number of cycles will cause failure, or a higher number of cycles, or a higher stress at a lower number of cycles will cause failure. So during the lifetime of the turbine, you get a huge variation in the amount of stress. And what you get is a summation of damage for each level of stress, and none of which would individually cause fatigue, but when they're all summed together over 20 years, they can cause failure. The fatigue data is supplied by the turbine suppliers, and it consists of hundreds of lines of data, each of which is a stress median, a stress range, and a number of cycles. So that data can vary from 250 to 2,000 to maybe 25,000 lines. And we used to analyze those with a spreadsheet, but it becomes very cumbersome when you get huge amounts of data. So about 2 years ago, we developed our own computer program for doing the fatigue analysis, which is this, and it allows us to do it very, very quickly and accurately. The basic parameters for the foundation are put in here, which will be the bore tension and various parameters. The fatigue data is read into the program. You can see this one has 352 lines of data. So this is the width, which is the range of the loading, the mean value, and the number of cycles, which can, in some cases, this particular one is 1 million cycles, 10 million cycles actually. So these are all the different elements of the foundation which are checked. These are the different things that you can check, different parts of the foundation. And for each one of those, there's a separate dialogue or a different method of analysis. This is one particular one where you, for checking steel tension, using moments as an input. And down here you can see that the damage summation was 10 to the minus 5. There's sometimes fatigue is not normally a problem. Sometimes we get damage summations of maybe 0.5, rarely more than that, but more often than not, it's like 10 to the minus 6 or less even. There's a finished foundation with the steel ready for pouring concrete. You can see there's huge quantity of steel. That's it. So,
Hi, my name is Cormac Murphy, Cormac Murphy, it's my official name. I'm with Malachy Walsh Partners 11 years ago, and I almost from day one ended up in Windfarms, and almost from day one ended up in Peat. My previous employer would have always said that I was never happy on a inside a hole of muck, but the tie coming in top of it, that was pretty much some of my attitude, and then it's where I've ended up afterwards. It's funny, my life turns around. I'm going to give a presentation on what it's like to build wind farms in Peat. It's a very difficult media to work in, and this is a typical wind farm in Ireland. They're all upland, almost all upland, and almost all of them are in Peat. And there's a very good reason for that. And there's the wind distribution for Ireland, and on the right you have the bog distribution of Ireland, and there's a very good correlation between them, and effectively all your wind is in your mountains and all your peat is up in all your blanket bog is up in your mountains. So if you want to work, if you're a consultant in Ireland, if you want to work in a civil engineer working in wind farms, you're going to be working in peat, so you kind of have to like it or get used to it. Problems associated with peat, they're difficult work conditions. You've significant habitat impact, and that as civil engineers we don't always consider that, but as engineers in wind farms, it's all our wind farms are in almost always pristine, semi-pristine areas, high value habitats. So we have to consider the environmental side of it. Other problems you've work practice initiated peat slides, you have man-made peat instability conditions, natural peat instability conditions, and peat, it's a very difficult material to assess. It behaves sometimes, I describe it behaves way better than you expect it to behave, and then the next minute it'll let you down with a wall. If you change it, it has many different qualities. And then one of the final problems is design certification in peat, and that's kind of where I'm going to finish up with. It's really difficult. These are typical of stuff we come across in wind farms all the time. Your roads are up on top of peat, and every time you step off your road, you're in trouble. And almost every single wind farm I've been on, at some stage of one of these, for some reason cranes are forever coming off the edge of the road, whether it's crane drivers or not, I don't know. Every wind farm I've been on, we've had to pull out a crane out of some stage. Diggers are constantly just one false move, and you have a digger gone in a hole. That was one of the top one there was a job here in Cork. That's in this turbine nacelle. That's like €1 million falling off the back of a truck, and that had to go and be replaced. And not easy on timelines that we've got. Now, if we get our peat strategy wrong, we can turn this into that, which is what we try and avoid. That was in County Kerry, I'm afraid, one of our own. Now, the instability conditions, the two main types. You have work practice initiated. Theoretically, these are used to prevent using experienced personnel and supervisors. In practice, that doesn't, that's all very well and good to say that, but it happens. Selecting appropriate construction methodology and in vigilance. And we had a mini boom in the wind industry a couple of years ago, and we have it now in consultancies, trying to get experienced people, trying to get the right people on the ground was very difficult, and it becomes a problem. Land use initiated are one of the most insidious ones, and I'm going to do a little bit on that. They're very difficult to spot on the ground, and landowners can be very slow to come forward with information. They can even mislead you. We've on multiple sites been told the ground is great, and it wasn't. And I'm going to go through one or two examples here. Over the years in Malachy, we've become very adept at spotting. There's indicators, and we're getting better at spotting. Aerial photography is I spend half my days poring over aerial photographers of different years, different areas. And of late, the Google and Bing area have become really, really good. This is the main one. The main problem we come across is sausage cutting. Doesn't sound like much, but it has a huge impact on a bog. And I'll just give you an example of what a sausage cutting machine looks like. It's effectively like this is. There's a bottom.
As in the back.
This is like a chainsaw that goes down into the bog. It pulls up peat and it extrudes it out the back of the machine. And the effect of that chainsawing is it totally destroys the integrity. Like I said earlier on, peat, when it behaves itself, it carries loads that you just couldn't imagine that it could carry. But as soon as you interfere with that top fabric of peat, it behaves completely differently. And here's just an example. You can actually see the individual cuts. This would have been sausage cut in that direction several times. The whole bog, as you see, it's fallen over. It has no integrity in one direction, so it's much stronger in one direction than the other. You think, but when you look at that on top, it looks the same, but it's completely it has completely different characteristics in two different directions when you're working with it. So if you're working in line with the cuts, you're in big trouble. You're going across the cuts, you won't even know they're there. But it is as simple as that. It carries no load. going longitudinally, and it'll carry a normal load going perpendicular to it. Very hard to deal with. This is the effect of it when normally that bog behaves like it's like a carpet on top of what's underneath it is. Soup is probably the best way of describing it. But the carpet on top is able to spread the load and carry the load really well. But when it's sausage cut, that's what you get. You literally have a vertical cut going down for the depth of that chainsaw, and the characteristics of it completely change. This is a picture of what happens when it does go. This is an area, this is the piece that I showed earlier on, it's the Malachy Hill above Tralee. And it's funny, as Sean said earlier, I stepped on the Wikipedia page, and the Wikipedia page is attributing Malachy Hill ramp site to Windfarm construction. The actual fact is that it's the sausage cutting of the peat that was the real reason for that. It wouldn't have gone if this peat had been completely sausage cut. I have an aerial view of that. This is aerial view from 2005. This was taken after this site. You can see where the whole place has been sausage cut, and as soon as one part went, the whole lot just unwrapped. I like to describe this as being, you come home with a sliced pan and a pound of sugar, put the sliced pan up on top of, well, you were all old enough to put a pound of sugar actually. You put a pound of sugar up on top of a sliced pan and it'll stay on top of it. Take the wrapper off the sliced pan and try and do the same thing, and it's not going to do it. So the low carrying capability of the peat is completely taken away when it's sausage cut. But as you can imagine, if you're going across this way, it still has a certain amount of capability, but going along the lines of it, it has zero strength. Like I said, over the years we've become very good at spotting how to find it. I almost got a nose right at this page. That was a job in Donegal. That was Cork, Limerick, Kerry. This machine came out in 1982. It was difficult. An Irish company designed it. Brilliant for harvesting peat. One-man job, way cheaper than very productive, but absolutely ruined bogs. And like I said, when we came to do wind farms, it took us a while to get the hang of this, to be able to spot these conditions that were going to give us real trouble. And just to move slightly on now from one of the things, what's changed over the years now is our ability to analyse an area. We've gotten much better models and stuff like that we can work with to actually analyse I'm just going to run quickly through just basics. I'm not going to spend long on feasibility because you've probably heard it all before. But we will take our 3D models and we'll analyse the slope. We get our surface slopes. We get our peat depths. This is a site in Galway. It's not particularly bad because the peat depths are pretty shallow most of it, but you have a combination of slopes. We combine those using the prescribed methodologies using infinite slope stability analysis. We run it through computer programs to create hazard risk zones, and you try and design your wind farm around the bad areas as best you can. We do another constructability assessment, which weights the thing differently from infinite slope stability analysis, which take more into account our experience. We say we apply higher factors to peat depth and slope. Again, when you're designing, you try and stay away from areas that are going to give you trouble. One of the changes that has come, one of the better things we're getting lately is GPR has come in a big way into Windfarm. So ground penetrating radar, instead of going out peat bombing, we're able to get very good subsurface profiles now, which make our models, our analysis models are much more reliable than they were, or they're giving you a better picture of what you're dealing with. So one of the, I'm just going to run through a particular wind farm that we just completed there lately. It kind of encapsulates all the problems that we get in working on peat. This is Tullahedal Wind Farm in North Kerry, and one of the things that we're coming up with, we have a lot of legacy planning applications. If you were to go out tomorrow now, you wouldn't try and put turbines in Tullahedal. The peat depths, you can see the peat depths there, right? We have greater than 6 meters. A significant 30% of that wind farm is in peat depths greater than 6 meters. Before we went to Tullahedal, we wouldn't, 4 meters was the deepest we'd ever come across, and we were faced with this place where you had over 50% of it was greater than 4 meters. Like most of that wind farm is in really deep peat. On top of that, we had sausage cutting. On top of that, I'm not sure if I can come back to that in a sec. We had an existing slide that we had to build over, our historical slide. So this is when we arrive at Peat, this is what we're faced into. We have to try and come up with our solutions, and then we have to certify it. Now, it's a tongue in cheek, but I know it works in practice. Now, if I can only get it to work in theory, that's a big problem in peat. It's not like soil geology, soil geotechnics. There's a world of knowledge out there and background, calculations that are available to people to certify, to analyze and certify ground conditions. It's just not there for peat, and it's very difficult to do it for peat because of the unpredictability or because of the variability. You have variable in the strengths in vertically, horizontally, it's thixotropic as well. Once you disturb it with vibration, it behaves differently to when it's static. Your water table is up and down the whole time. It's a difficult material to do certification in. And we have to work with heavy machinery. All our hard stands have to take a 1,000-ton crane. You're putting the shaman through there, like you've a 75-meter hub height is your average hub height here in Ireland. You're having to put a 70-ton nacelle up on top of a 75-meter stick. The loadings for the cranes and the hard stands is huge, and it's fine for the overturning of a piling rig, and for we piling as well. But the amount of risk is you've only a driver and an attendant. But when you've a crane putting up a turbine, there's a heap of men around this. You just can't get it wrong. So we end up with we still have to try and certify it, but we end up with much more conservative designs. Just go back to Tunnel again, just to show you a couple of things. We'll say again, on plan view, like this turbine T5 is over 8 meters of peat. In fact, when the lads were digging it out there, and there was 9 in parts of it. This here was a peat slide from 1870. We had to go across that into the scar of the peat of the slide. All this section here was all sausage cut. This is all sausage cut. This is the here's the air photograph of T1. So you can see here this slid in according to what I could find out was in 720. I've had different readings, 1869, 1870. But this area slid and down into Ballylongford, blocked the bridge in Ballylongford. So peat slides are not new to wind farms; they've been happening all along. But this is the remnant scars. You can see all these circles. Every one of those is where the peat tore apart 100 years ago and then grew back over again. Very hard to spot on the ground when you're walking across it, but when you load it, it behaved itself pretty quickly. Traditionally, or when I say traditionally, but in Ireland we've always done what's called floating roads. But our floating roads, when peat gets in excess of 2.5 meters, the traditional stone-based floating road using geotechnics, that's fine until they start to go. And there's a road that has punched through the top part of it. There was a drain dug here and a drain here, and the peat just rode down with it. And we had to stop and think again. Now, our solution, it was we had done this once before on a real small section in Windfarm, and we sat down with our contractor and we said, lads, there's no way we can guarantee these roads are going to stay up on top of 6, 7, 8 meters of peat. So we had this was in the back of our heads. It was a lightweight floating road that replaced aggregate. We used logs instead of aggregate. It's a really old technique, goes back to prehistoric times. We introduced geogrid into it. The principle was that as this road would sink, the buoyancy of the timber of Douglas fir is around 0.7. So when it sinks, it goes from being a weight to a positive buoyancy. So it limits your long-term settlement of the roads. It also, the fact that timber has tensile capacity, if you have to spread our loads over much wider areas than we were getting with stone. And stone, you're depending on just on the 45-degree load spread, and the geogrid had to kind of spread it a little bit further. Whereas with logs, we were getting 5 meters this way, 5 meters that way, and then we were able to spread it longitudinally as well. But you had the safe knowledge in the long term that in the long term settlement would be controlled through the buoyancy. So we put stone on top of it because you have to get traction, you have to have a road for the turbine deliveries to come in normal with standard wheel trucks. So we had to put aggregate on top of it. So we limited our aggregate. We did a balance check on being able to ensure that the buoyancy would match the downward, taking into account that the peat had some amount of strength. Now we did kilometers of it. We went the only time we'd ever used it before, we did 50 meters across a flush in Peat. We did kilometers of it. Now the contractor had to get on board with us, but we did the first one, and we had to modify. We had to learn as we went along. We had no calculations for it. We had no precedent. We had nothing. All we had to do is we had to get there. We had to figure out something that was going to get 100-ton loads in across 6-7 meters of bog. Came up with our own way to do it. The lads in site started getting forwarders in, putting out timber. One thing, we switched from geogrid to combi grid. I'm not sure if are any of you working in geotechnics or civil or heavy civils or any that kind of thing. The robustness of combi grid compared to the salesmen when they come in selling you geotechnics, they all have their different speeds. But what we're finding is that the combi grids are so much more damage resistant than grids. If I could go back to that other for you, would actually see there at the bottom corner of this. We bust a lot of we found the grids were breaking. We didn't bust a single of the ones. We switched to combi grid. We never had any of those type of problems. Again, the combi grid it just seems to be able to resist damage. Now, this will give you an indication of that section road was being built over the place going into where the side was before. That's only a 12-ton digger, and he's sinking on top of the logs down to water level. So your water level is at ground level. We're bringing in stuff with low ground pressure machines. Now remember, we have to bring 100 tons and more across that bog that you can hardly walk in. We persevered, kept going, got our roads built. We looked at the one cable. This thing here, this was actually a cable run because you have to carry your cables from turbine to turbine. They can't slip. They can't go under. So we had to float our cables along as well. Now we're in there. This has never been done before, never tried before, and we had to prove to the client and prove to the guys that live in the wind turbines that it was going to work. And the only way we could come up with was to do proof flow testing. So we ran trains of A40s and A35s. So like that's an A35, that's running there at 55 tons loaded. That's an A40, that's 60 ton loaded. So the two rows, and there'll be another one behind. We did proof runs with the turbine manufacturer, with the guy who was going to deliver the turbine, and said, right, look, walk along with us. This is what they're doing. This is how they're spreading load. So you're looking at 130 ton there over the length of 2 dump trucks. And the slide I showed you earlier on, the road failed under its own weight. Yet here we're getting such a load spread with the longitudinal and transverse logs and the geogrid. And there's probably other slides I didn't bring in, but the amount of tonnage of stone that they shifted was just astronomical. I didn't bring the few. I can't show all my dirty underwear. So that was the first section, the floater roads. Now I should actually have brought over and back. Here we were faced into. I was thinking about landowners not telling you the truth. One of the other turbines, T6. We came off of a cutaway bog here into here, started digging, and the whole lot was sausage cut. Now the landowner had swore blind, the developer, the person who put together the project, swore blind that it hadn't been sausage cut. First bucket in the ground, and the ground just started coming. It was all sausage cut. And as Winston Churchill said, if you're going through hell, You just got to keep going, and that's what the contractor did. Now we also have to build a turbine base inside in that Peat, and the only way the lads had at the time was to put up. They had the techniques of excavate and replace. You build a stone berm around to create a cofferdam, dig out, go down. This now, like, that's a 20-ton digger. That's not a mini digger. That's a 20-ton machine down at the bottom of a hole for a 22-meter diameter base. A lot of material. That was 7 meters of upfill. That was the deepest one we did. After that, we switched to piling. But I'm at ground level. Like that. This isn't looking up. This is looking down into that hole. The ground level is above you. So you've, I think, 4 or 5 meters of peat being held back by our that was a typical texture. So you've a rockfill berm holding back the peat while you dig out and upfill your turbine base. I threw in some calc systems, so you wouldn't think it was just comic books that I read the whole time. Like there is, we did do some calcs for what we could do, but that was on the rockfill. This is that turbine now, and I'll talk about environmental impact later on. Like the photograph I showed you of the digger, he was starting there, and all this block, this whole piece here was sausage cut the whole way across there, and that just ran. And this was the extent. Now remember, that is 70 meters. The bog ran for another 40 meters before we could get it stopped. But we just had to keep going. And we put in a restoration plan to get it back to it got restored. But at that stage, we were only in 4 meters, 5 meters of peat there, 5 going to 6. And we knew we still hadn't gone to T5 at that stage. So we needed to have a change of plan. And the next one had to be cofferdammed. Now this was an 8 meters of peat. Again, I go back to your problem with sheet piling is you have to put in the sheet piles, you have to extract the sheet piles, so you need a hard stand to put the piles in from, up on top of 8 meters of peat. So again, we got our thinking hats out, and we had a small bit of thing. Most of the loading, when you start doing type of work design starts for piling rigs, the largest loading is in extraction of the piling hammer. So we separated those two. We totally integrated temporary and permanent work designs, and we said, right, we're only going to install the piles off of our temporary floated hard stand, and we're going to extract them off the permanent rockfill. And that allowed us to do away, let's say the contractor hadn't taken for any of this piling, so we're faced with, we can't go back to what we had done the other one. He had to sheet pile, but the temporary works for propping it and for bracing it and whaling it, I think he got a quote of $250,000 for the bracing for a job he hadn't priced. He was stuck in, he hadn't priced cofferdamming it, he hadn't priced brace, so we had to figure out a way to get rid of the bracing. Not easy with an 8 meter deep peat. So the first thing we did was separated the requirements for installation, pile installation, and pile extraction. So we said, right, this only has to take the eccentricity of the piling hammer and the pile. He only has to hold them. He doesn't have to pull them back up again. So we had a definite weight, and we were able to spread that weight over our toggle. These block mats are spread in 2 directions. We were able to put a track on each section to get our weights, and then prove it. Again, it was empirically proven rather than mathematically proven. It was empirically proven. Now those piles then had to be extracted, and we had to figure out how we're going to hold the stone after we pulled the piles was another issue. So we did an upside down geogrid situation. We put the geogrid on top, which sounds bizarre when you say it first. It might sound bizarre to me when I said it out loud as well. And the idea was that when you pull the pile, you lose a certain amount of stone, but as that stone is lost, the geogrid on top will drape down and apply a retaining pressure in the other direction, limiting the amount of variability lost. Now, we had to give certainty of bearing capacity of 250 kPa. This is our main crane had to get set up here. So there's the load path. We put 80 degrees down through the geogrid, that was by the manufacturers, and then we took a 45 degree to the toe of the pile. And that was it. So we guaranteed, we set back the bearing strata from the toe of the pile, and again, proof of pudding is in eating. We know maths for this either. The proof of pudding is in eating. That is a 50-ton digger. I can't zoom in now, but this section is reinforced. We only did it on the perimeter. This section is reinforced. This is not. When you pull the piles, the bit that's not reinforced went away, but the reinforcement, he's sitting up the top of that line of geogrid over 8 meters of fill, digging out the peat in front of him, and that whole temporary works thing worked out a dream actually, and in the sense that again, there's our temporary works. Our pile extraction was done after we completed the hard stand. The piles were extracted off the completed hard stand rather than off the temporary works. We then had to get a piling rig in there. Now, the original temporary works design kept the piles for the piling rig, but this earth reinforcement had worked so well that the lads decided to continue it around, and that allowed them to extract the piles and off-hire the piles while the permanent piling was going on, while the rotary core piling for the turbine base was going on. We were able to extract the piles and off-hire them. So the piling got completed. You can see the radius impact. The impact was limited directly to the footprint of our works, whereas in the previous one where we had gone straight in, they went for 60, 70 meters outside of it. There was virtually, like the situation here was when the pile was, they just lay out the piles, and when the piling hammer would pick up the pile, you used to drag along the bog. That was the extent, to some extent, of our damage was some drag marks from the piles. So like there's a turbine being put up. Like I said, that's a 1,200 ton lever LTM 11200, picking up the rotor, putting on the nacelle is 70 or 80 ton on its own. But as you can see, the whole thing restored very well. There's the head of that slide. They're all the marks from the scars from the previous slide. I say if you actually want something done, tell an engineer it can't be done, and they'll figure out how. And that's pretty much what went on there. We said, how we never got it? It shouldn't have been able to be done, but we got there in the end. The lads on site, I couldn't say enough. He's going to become a legend in his own lifetime. The foreman, Arthur Moynihan, like some of the stuff that they had to try and do off the cuff in really different conditions. But it took a team. Anybody who knows myself and Taglieri's relationship will know that it's hard for me to give him praise that's due to him. But the PSDP and the owner's engineer had to join forces with us to get that thing done, to get stuff across. They had to trust that the contractor was going to do what the engineer designed to the extent that he was going to do it. That without that full circle of cooperation and trust, we would not have gotten that job across the line. Like you're like I said, none of the floater roads, none of the log roads have been proven before. That upside down hard stand hadn't been done before. I was aware of it. I don't know, maybe I'd done some stuff like that before in marine engineering, but not to the same extent, and not as critical as what we did there. But it was a team effort across the whole thing, and I couldn't speak high enough for the two lads that ran the team for Moriarty's on the ground. That's the end of my slideshow. I have a fly through. I would have drawn if anybody wants to see it, but it's probably gone a bit late, I think, is it? Yeah. Okay. All right. Okay.
Thanks very much to the three of you for a fabulous talk. It's something quite out of the ordinary. We don't often get talks of that caliber. It's been excellent and quite something that we're not used to hearing about. 2.9 metre long holding down bolts and bending moments, the equivalent of 100 tons at the end of a 100 metre long cantilever, and so on. I could go on and talk about the lightweight floating access road detail that we just heard about, which was very interesting on using Douglas for INOT, so that's all very interesting. We have time for just one or two very brief questions, bearing in mind our speakers have a long way to travel when they get out of here tonight. So perhaps, do we have a question from the audience before we allow our speakers to get away? Any hands up for the first question? Yes, we're all the way at the very, very back. Sorry, would you wait one moment, because we're webcasting, so in order to hear what's being said, you need to use the microphone, please.
Hi, this is Olivia from Malachy. Question for I suppose that last chart you explained, which was very interesting. How did it come in, or how did it affect the overall construction program and the final costs?
Program was down to the wire. You might not see. I've other photographs that will show the turbines going up on one hard stand while we were still piling. The concrete piling was still being done. Now, if you're still piling while you're putting up turbines, you're in trouble program-wise. And it was down to the wire program-wise. Cost-wise, there's a man below there that knows better than me. I'd say hard to know. The contractor knew that there was some Peat there, had put some money against it. I don't think he had anticipated that. I think they were okay with the floater roads. The piling caught them. They weren't expecting that. So that would have worked. If we had to conventionally brace that like a normal copper dam, we were done for. Sorry, they would have lost a lot of money. I think I can't remember off the top of my head. I don't know. I think by doing was the order of 200,000 on bracing alone. Forget about the hire and installation costs. We took that off they actually ended up piling that themselves. They just hired the piles because the cost no one else would certify it. Any of the piling, trench control, none of them would touch it because they wouldn't certify it without bracing it. So we had to take on that on the chin, and they took on the installation and hiring up the actual machine and piles.
Right. Okay. Thanks very much. Can we move on? Anybody else got a question? Yep. Yes, Paul Collins.
Maybe Brian or Sean, you may have spoken about it already. The use of the embedded cans, particularly like the Enercon and Vestas, is a current practice too, given the problems that they're having over the years.
I think, Paul, that Enercon probably announced in a meeting once that the last Windfarm we're going to see cans on. I'm not sure the developer of that Windfarm swim fest, but that was probably 2 years ago. I haven't seen ones.
Even the E70's gone to unknown walls now. We did a project up in Palace, which was kind of the last of the E70s, and it was all unknown walls. So they're pretty much gone from cans.
Okay. Right. Yeah. Down at another question from the back from Mr. Casey.
In terms of the guidance documents that you use for the design of wind turbine foundations, because they're not directly covered by the Euro codes, what do you use for that?
We'll take that. Anybody? Sean, can you take
there's
that?
overriding documents, the manager Lloyd, what's the name of it? To design the window lines. It's kind of an overarching document, but the structural design is still not using all of those. But there's another document.
Model Code 1990 is used for fatigue. Fatigue is poorly covered in the Euro codes. It's just not up to the kind of cyclical loading that you get in the turbines. So Model Code 1990 is used for that. It is a kind of a mix and match of a whole lot of different documents. It is kind of early stages for 15 years in. It's the early stages for the industry. lot of designers are kind of trying to catch up with, in fact, the codes are trying to catch up with the designers over the point.
Okay, any other questions before we wrap up? Okay, very good, we leave it at so. I'd like to say a very big thank you to Brian, Sean and Cormac for putting together what has been a very, very interesting lecture this evening. I know that they've put a lot of time and effort into it and they've travelled a long way this evening to come and deliver it to us. So we appreciate that very much. So thank you very much, the three of you, and I would ask you please to show your appreciation in the usual way.